You've probably been here before, a sealed glass jar with a metal lid refusing to budge. But run that stubborn lid under some hot water for a minute, and it suddenly twists right off. This occurs because of a predictable physical principle. Matter typically increases in size as temperature rises. We rely on this growth to measure temperature itself. In a laboratory thermometer, warm fluid transfers heat to the liquid inside the glass, usually alcohol or mercury. As that liquid warms, its volume increases and it climbs up the narrow tube. Invisible gases follow the same rule. If you leave a partially deflated balloon in a warm sunbeam, the air inside heats up and pushes outward, pulling the rubber skin completely taut. This universal behavior is known as thermal expansion. While it's easy to observe in everyday life, utilizing it for complex engineering requires moving beyond general observation into mathematical precision. To understand how to harness this force, we have to look at the math behind the expansion. Imagine a simple metal rod. If we increase the temperature, it extends by a tiny fraction. We measure this using the coefficient of linear expansion, alpha sub L. This constant value tells us exactly how much its length changes for every degree of temperature shifted. A flat metal sheet expands along its length and breadth simultaneously. Calculating this new area reveals a tiny overlapping corner. Because the expansion is so small, this fraction is near zero, so we drop it from the calculation without losing accuracy. With that tiny corner removed, the math simplifies into a clear rule. The coefficient of area expansion is exactly twice the linear expansion. Theoretical planes eventually give way to the three-dimensional objects that make up our physical world. A solid block expands equally in length, width, and height when heated. Multiplying these dimensions creates a complex algebraic progression. Discarding the negligible overlapping fractions reveals a simple relationship. The coefficient of volume expansion, alpha sub v, is exactly 3 times the linear expansion. This means that knowing just one material constant allows us to predict how any complex three-dimensional object will swell when heated. While this rule of expansion is nearly universal, water possesses a unique physical glitch that is essential for life on Earth. This chart shows how the volume of water changes as it warms. Unlike other substances, water actually contracts as it heats from 0 to 4 degrees Celsius. At its lowest volume, water is at its most dense, causing 4-degree water to sink rather than float. In a freezing lake, that heavy 4-degree water sinks to the bottom. The colder, lighter water floats to the top and turns to ice, creating an insulating lid over the liquid below. This specific anomaly is the primary reason aquatic ecosystems do not freeze solid in the winter, allowing life to persist in the liquid water at the bottom. These mechanics offer solutions to practical human challenges, such as the assembly of a wagon wheel. A blacksmith needs to fit a metal tire onto a wooden rim. The iron ring measures 5.231 meters, but the wheel it must cover is 5.243 meters. At room temperature, there is a 12-millimeter physical gap preventing the fit. To bridge that 12-millimeter difference, the blacksmith applies the expansion formula. Factoring in the specific growth rate of iron, he calculates a 218 degrees Celsius target will stretch the metal far enough to clear the wood. Once in place, he douses the expanded ring with cold water. The iron rapidly cools and contracts, locking onto the wood with an unbreakable grip. By quantifying exactly how heat alters the physical world, we can turn a simple property of matter into a precise and powerful assembly tool.